Hello and welcome to this video on periodic functions and how to determine their Laplace transform. So what is a periodic function? It's a function that repeats, roughly speaking. Take sine of t for example. Sine of t looks like this on the interval from 0 to 2 pi, and then the same pattern repeats. The same thing happens with cosine. The function looks like this, and then the same pattern this repeats. The time to pi here is called the period of the function. One more example is the rectified sine wave, absolute value of sine of t. So from 0 to pi, the function looks like this, and then the same pattern repeats. We'll give a proper definition in a moment. Just let me highlight at this point that all we need to know is how the function behaves over an interval from time 0 to time t. If you know this and you know that the function just repeats, then you can tell the value of the function at any future time. Let me just quickly mention another example are these PWM signals that are very popular in electrical engineering. Now, let's have a look at the definition of a periodic function. We say that the function is t periodic, or is periodic with a period t. If this happens, this is what we mean by the function repeats. The function at time t plus big T is equal to the value of the function at the current time t. And this holds for all t. And we can verify also algebraically that the above functions, the functions I mentioned above, are indeed periodic. Let's look just at sine. Sine at t plus 2 pi is equal to sine of t. So this is 2 pi periodic. 2 pi is here. And let's look at the last one. If you take the absolute value of sine of t plus pi, sine of t plus pi gives you minus sine of t. But you don't need the minus here because you have the absolute value. So this is the absolute value of sine. So the function here is pi periodic. Right. Now there is this beautiful result that allows us to determine the Laplace transform of periodic functions using a very simple formula. So if you have a function f, which is periodic with period t, then we can define this new function, we call it f naught. And this function is equal to f times 1 minus the Heaviside with parameter t. Now I believe this looks familiar because this is exactly what we discussed in the previous video on functions defined piecewise. And we said that if you have a function defined piecewise, then you can write it in terms of the Heaviside function. And once you do this, then you can determine the Laplace transform. So if you go back to the previous video, you'll see that you can determine the Laplace transform of such functions. And let's call the Laplace of f naught, let's call it big F naught, uppercase. Now there is this formula that says the Laplace transform of your periodic function f is equal to the Laplace of f naught divided by 1 minus the exponential of minus s times t. I have a little note here to mention about f. You don't need a formula for f over all the non-negative numbers. You just need a formula that works on the interval from 0 to t. And the reason is that after time t, this whole term becomes 0. So you only need a formula that works over the interval from 0 to t, and that's often a lot easier to obtain. I want us now to have a look at two examples. Example number one is this function here, which is equal to 1 up to some time t, and then it goes down to minus 1. The period of this function is 2t, because look, you have this pattern from time 0 to time 2t, and this pattern repeats. So we have a period of 2t. So that was the first step. The second step is to come up with a formula for f. So this function f is defined piecewise. Let me just delete everything after 2t. All we care about is this part of the function from 0 to time 2t. So a formula that describes this function, which is defined piecewise, is 1 minus 2 times the Heaviside function with parameter t. We can now define f naught of the theorem, and this f naught is my function f, times 1 minus the Heaviside with parameter equal to the period of the function, which is 2t. I'm substituting in f, which is 1 minus 2 times the Heaviside, and I now have this product, this times this. Well, alright, we can do the distributive property and expand. So you end up with this, where the interesting term is Heaviside at time t times Heaviside at time 2t. What is this now? Let's have a look. The Heaviside at time t is a function that goes to 0 after t. The Heaviside at time 2t is this, goes to 0 after 2t. And now you multiply these two functions together, and they're equal to, well, of course, this function, which is Heaviside with parameter 2t. So we can simplify this. This becomes Heaviside with parameter 2t, and we can combine this term with this term and end up with this. So this is our f naught. Now it's not difficult to determine the Laplace transform of f naught. We call it big F naught of s, the Laplace transform of this, and using basic using the table of Laplace transforms, we end up with this expression. Essentially, we're done now. Let me scroll up to show you the theorem. So the theorem says, once you have determined the Laplace of f naught, just divide by this, and you have the Laplace of f. So let's have a look. This is the Laplace of f naught. I have just simplified it over here. So the Laplace of f is the Laplace of f naught divided by 1 minus the exponential of minus period. Don't forget the period is 2t times s, and that's it. You can stop here if you like. So that's a perfectly legit answer. Or you can do a little more work to simplify the result. That's optional, only if you like, to write it like this: 1 over s times hyperbolic tangent of t times s over 2. And this was the first example, but I'd like us to have a look at another example. This one over here, where we'll have a little bit of trigonometry, just a little bit. So this is the absolute value of sine, and we see that this is a function with period pi, periodic function with period pi. We said all we need is a formula that describes the function from 0 to pi, so I'm going to just delete the rest of the function. And the question now is, what is this function? Well, this function is just sine of t without the absolute value. And that's very convenient. So this is the formula for time from 0 to time pi equal to sine of t. And we define f naught, which is f times 1 minus Heaviside with parameter equal to the period of the function, in this case pi. So it is sine times 1 minus h pi. Okay, multiply, do the distributive property, sine of t minus sine of t times Heaviside with parameter pi. And now recall that for us to be able to determine the Laplace of this term, we don't like this t here. We really would like this to be sine of t minus pi. But the sine of t minus pi is really equal to minus sine of t. So this minus sine of t you can write as sine of t minus pi. So plus here, sine t minus pi, great. Sine, when you take the Laplace transform, gives you this. And then sine times Heaviside with parameter p gives you this. That's from the previous video. So overall, you can kind of combine the two fractions together, and you can write the Laplace transform of f naught like this. Now from the theorem, this is theorem 425 in the textbook, you have that the Laplace transform of the periodic function f, absolute value of sine, is the Laplace transform of f naught divided by 1 minus exponential of minus pi s. And if you like, you can simplify and make it more elegant, whatever. I'll leave this to you if you like, but you can even stop here. So that was it for now. Thank you very much for watching, and see you.